Hey chemistry, and welcome to our second to last chem lesson of the entire year. You're so close. Okay, so today we're going to talk about colligative properties of solutions. So we've talked about solutes, we've talked about solvents, now we're going to talk about other properties. So physical properties of solutions that are affected by the number of particles, but not the identity of dissolved solute particles are called colligative particles. Sorry, a lot of words. The word colligative means depending on the collection. So colligative properties include four things: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So let's talk about electrolytes and colligative properties. So in chapter 8, we learned that ionic compounds are called electrolytes because they dissociate in water to form a solution that conducts electric current. Some molecular compounds ionize in water and are also electrolytes. Those that produce only a few ions in solutions are called weak electrolytes. Sodium chloride, for example, table salt, is a strong electrolyte. It almost completely dissociates in solution, producing Na plus and Cl minus ions. Dissolving 1 mole of NaCl in a kilogram of water does not yield a 1 molality solution of ions. Rather, there would be almost 2 moles of solute particles in the solution. 1 mole each of Na plus ions and 1 mole of Cl minus ions. So let's talk about non-electrolytes in aqueous solutions for a second. Many molecular compounds dissolve in solvents but do not ionize. Such solutions do not conduct an electric current, and these solutes are called non-electrolytes. Sucrose is an example of a non-electrolyte. A 1 molality sucrose solution contains only 1 mole of sucrose particles. There's a picture, figure 1516, compares the conductivity of a solution containing an electrolyte solution with a solution containing a non-electrolyte solute. So you can see one of them lights the light bulb because electricity is able to be conducted. So again, colligative properties depend on the collection. They are affected by the number of particles, but not the identity of the dissolved particles. So one is vapor pressure lowering. Okay, in chapter 13 you learned that vapor pressure is the pressure exerted in a closed container by liquid particles that have escaped the liquid surface and entered the gaseous state. In a closed container at constant temperature and pressure, the solvent particles reach a state of dynamic equilibrium. So they're still moving, but there's no net change. This escaping and the re-entering of liquid state happens at the same rate. So the same number of particles are escaping as are re-entering at all times. Experiments show that adding a non-volatile solute, which is one that has little tendency to become a gas, to a solvent lowers the solvent's vapor pressure. The particles that produce vapor pressure escape the liquid phase at its surface. When a solvent is pure, its particles occupy the entire surface area. But when the solvent contains solute, as shown in 17b, a mix of solute and solvent particles occupy the surface area. With fewer solvent particles at the surface, fewer particles enter the gaseous state, and it lowers the vapor pressure. So the greater the number of solute particles in a solvent, the lower the resulting vapor pressure. Thus, vapor pressure lowering is due to the number of solute particles and is a colligative property of solutions. Okay, so again, the greater the number of solute particles, so the more solute particles, the lower the vapor pressure. Okay. You can probably predict the relative effect of a solute on vapor pressure based on whether or not the solute is an electrolyte or a non-electrolyte. For example, 1 mole each of the solvated non-electrolytes, glucose, sucrose, and ethanol, have the same relative effect on vapor pressure. But 1 mole each of solvated electrolytes, sodium chloride, sodium sulfate, aluminum chloride, that's a greater effect because there's a greater number of ions there. Okay? So, key point is if something is an electrolyte, if something ionizes in a solution, then its very molecular structure comes apart. The ions are no longer bonded together. You no longer have table salt in there. You just have some sodiums and some chlorines. They're off on their own. Okay? That's the difference. It means there's more particles. Sucrose, when it dissolves, or glucose, the individual sucrose particles are still bonded together. You don't have carbons and oxygens and hydrogens floating around. You have the carbon, oxygen, hydrogen, sucrose floating around. That's the difference, okay? So, colligative property number 2 is boiling point elevation. Okay, so because a solute lowers a solvent's vapor pressure, it also affects the boiling point. Recall from chapter 13 that a liquid in a pot on your stove boils when its vapor pressure equals its atmospheric pressure. When the temperature of a solution containing a non-volatile solute is raised to the boiling point of a pure solvent, the resulting vapor pressure is still less than the atmospheric pressure and it won't boil. Thus, the solution must be heated to a higher temperature to supply the additional kinetic energy needed to raise the vapor pressure so that it boils. So, this means basically that the pure solvent's boiling point needs to be elevated in order for it to boil at all. For non-electrolytes, the value of the boiling point elevation, which is change in temperature, delta T, is directly proportional to the solution's molality. So your equation is going to be change in temperature, that little b is boiling, equals Km. Note the m's a little italicized. The molal boiling point elevation constant Kb is the difference in boiling point between a 1 molal non-volatile non-electrolyte solution and a pure solvent. It's expressed in units of degrees Celsius over molal. And there's a little table in your book on page 472 that gives you the boiling point and the boiling point elevation constant. So for example, your water, Kb for water, is 0.512 degrees Celsius over molal. Okay? So every substance has a K constant. And you have a chart on page 472 that you're going to need for your Junopod in order to find the K constant. Then, of course, the M is your molality. Values of Kb for several common solvents, like I said, found in that table on page 472. Note that water's Kb is 0.512. This means that in a 1 molal aqueous solution containing a non-volatile non-electrolyte solute, boils at 100.512 degrees Celsius, a temperature 0.512 degrees higher than the boiling point. Okay, so what does those mean? Your constant is going to be higher, so that's going to be your change. Okay, so if we want to know the change in temperature from water's normal boiling point to from water's normal boiling point to water's boiling point in a 1 molal solution, your change in temperature is going to equal, K is the constant, 0.512, and if it's 1 molal, it'll equal that. So your change in temperature equals 0.512. Your original boiling point is 100 degrees Celsius, plus your change in boiling point, which is 0.512. So 100 plus 0.512 equals 100.512 degrees Celsius. So because it's a 1 molal solution, you plug a 1 in there, that's your constant. Your change, that means you have to add that to the original. Okay? So like vapor pressure lowering, boiling point elevation is a colligative property. The value of the boiling point elevation is directly proportional to the solution solute molality. So the greater number of the solute particles, the greater the boiling point elevation. Now, we have another one. Freezing point depression. What do you think it means? It means that the freezing point is going to go down. At a solvent's freezing point temperature, the particles no longer have sufficient kinetic energy to overcome the interparticle attraction forces. So the particles form into that more solid state. That's why things freeze. This prevents the solvent, but in a solution, the solute particles interfere with the attractive forces, which prevents the solution from entering the solid state at the normal freezing point. So the freezing point of a solution is always going to be lower than the freezing point of a pure solvent. So if you actually look at the chart on page 473, you recall looking at the phase diagrams where you can see the difference between a solid, a liquid, and a gas. You see some dotted lines on there that are going to show you the difference between pure water and the solution. You see that it boils at a higher temperature and freezes at a lower temperature than it used to. So, and the freezing point depression can be calculated the same way. The change in temperature for freezing is going to be a freezing constant times the molality. Okay, your freezing constants are on page 474. So KB are going to be on page 472. Your freezing constants are on page 474. Again, this is your change in, okay? So it doesn't mean it's going to freeze, water's going to freeze at a temperature of 1 degree Celsius. It means it's going to freeze that much lower, okay? So values of Kf for the common solvents are in that table. In using the delta T relationships, you must make sure to use the effective molality. So 1 mole of the electrolyte sodium chloride forms 1 mole of Na ions and 1 mole of Cl ions. So a 1 molal aqueous NaCl solution produces 2 moles of solute, making it a 2M solution, 2 molal. Because of this, 2 molal and not 1 molal has to be used, okay? So if it is an electrolyte volatile solution, then it's going to be different. You have to calculate that in, okay? So let's do one example problem, and then I will tell you about osmosis and osmotic pressure, and we'll be done. Okay, so what are the boiling point and freezing point of a 0.029 molal aqueous solution of sodium chloride? Okay, so now, first of all, sodium chloride is an electrolyte solution. If it says non-electrolyte, then you just take the molality as it is and calculate it, like up here. It was a 1 molal solution of, all done. But this is sodium chloride, okay? So our molality equals 1m of NaCl, but it's electrolyte. So we have to multiply it by 2. So our solution, sorry, it was 0.029. So 0.029 times 2 is going to be 0.058, and that is the actual molality of the solution. But remember, that's only for electrolyte solutions. If it's a non-electrolyte solution, you take the molality they give you and you go from there, okay? So let's calculate things in. It says it's an aqueous solution of sodium chloride, which means our solvent is going to be water. So the K constant we're going to use is the constant for water. So let's do boiling first, okay? So our change in temperature for boiling equals our K constant, which is 0.512 because it's water, because it's aqueous, times our molality, which is sorry, that should have a 0 in front of it, 0.058. So 0.512 times 0.058 gives us 0.003 degrees Celsius difference. Then our change for freezing point. Let's see, the K constant for water for freezing is 1.86 times our molality is 0.058. We already know that. 1.86 times 0.058 equals 0.11 degrees Celsius. Now we got to add it. So our boiling point of this, our normal boiling point of water is 100 degrees Celsius plus 0.03 equals 100.03 degrees Celsius. And then freezing temperature, the normal freezing temperature, oh dear, we are off the screen. There we go. The normal freezing temperature of water is 0 degrees Celsius. This is going to be minus 0.11 degrees Celsius equals negative 0.11 degrees Celsius. Okay? So you take, yes, you can see that. you use your equations to calculate the change in, and then you go from the original one plus your change, and that equals the temperature. So osmosis and osmotic pressure, I'm not going to write this down. Osmosis is the diffusion of solvent particles across a semi-permeable membrane from an area of higher concentration to low concentration, right? We know about osmosis. We talked about it before. So semi-permeable membrane means that it's a barrier, but there's holes through which something can pass. Okay, so like a semi-permeable membrane might be like a tissue or a washcloth, where when you pour water on one side, water will go through to the other side. Okay, so osmosis plays an important role in many biological systems. So kidney dialysis, plants taking up nutrients, that's osmosis. But let's say we talk about like a system. We've got sucrose water, and it's separated from water by a permeable membrane, semi-permeable membrane. So you have sucrose water, and then you have pure water, and you have a semi-permeable membrane between them. Both the water and sugar molecules are contacting the membrane on the sucrose solution, but only water is contacting on the other side. So more water molecules are going to be crossing the membrane from the pure solvent side. So the additional water molecules are going to create pressure and push water molecules back across the membrane. So the additional pressure is called osmotic pressure. Osmotic pressure also depends on the number of solute particles, therefore it's another colligative property. Okay? So that's the end. Quite frankly, if you don't know the words solute, solvent, solution, molarity, and molality, you need to go back and you need to redo the vocab stuff, because nothing in this lecture is going to make any sense. Not redo the vocab stuff, but look at the vocab again until you understand what it is, because none of what I just said is going to make any sense otherwise. Okay? So with that said, good luck on your colligative properties. It's a shorter Junopod. There's like 4, maybe 6 questions. Okay, so with that being said, good luck, and you will have your very last lesson on Monday. Bye, guys.